Okay, so we are finishing up section 2.5 with this intermediate value theorem. In the last video, we got the statement of our theorem. We saw that our function f of x really does need to be continuous to make this work. So now we're going to look at what we can use this theorem for. All right. And one of the main things we're going to use the IVT for is to show the existence of roots of a function. So we can use the IVT to show that a function has a root within some interval of values. All right, so first, to refresh, remind yourself, what is a root of a function? You might have a couple different definitions for this, depending how you remember it best. But remember, your roots are where the function crosses the x-axis, so that's a root right there. And so roots are anywhere that the value of the function equals 0. F of x equals 0 at a root. All right. A y value of 0, f of x equals 0, where the function crosses the x-axis. All of these mean the same thing, so that's a root there for some function. Okay, so how does this tie into our intermediate value theorem? Well, turns out that we can use the intermediate value theorem and just say that the particular y value that we care about is going to be 0. So we are going to be trying to show that there's a number c in some interval where f of c equals 0 for our y naught value. And that's the tie-in there. Okay, so use the IVT with y naught equals 0. Okay, so that means we are trying to show that y naught is between f of a and f of b. So f of a and f of b, that interval contains the value y naught, which equals 0. Okay, so what happens there, if an interval is going to contain 0, that means that part of the interval is going to need to be positive, and part of the interval, the other boundary of that interval, is going to need to be negative. That way we can cover 0 in the middle. And that's exactly what we're going to do here. If we can show for our function that we're looking at the interval a to b, and let's say f of a is positive and f of b is negative, or vice versa. All right, could be the other way around. As long as our function f of x is continuous on that interval, then we must have a root somewhere in this interval from a to b. So to draw a continuous function here, that's continuous, and we see that we do actually have a root here. That c value right there, that is a root of our function. Okay, and so that's done by letting our y naught value be 0. Okay, so this is what we're going to do. We need to show that one of the x values has a positive y value, and one of them has a negative y value, and that the function is continuous. So that's what we're going to do here in our example. Use the intermediate value theorem to show that f of x equals x minus 3 squared minus 7 has a root between x equals 5 and x equals 6. Okay. So if we want to kind of rephrase this in terms of the intermediate value theorem, what our goal is to show that there is a number c in the interval from a to b, so that would be 5 to 6. All right, that's our interval of x values. Okay, show that there is a number c in the interval from 5 to 6 where f of c equals 0. That's showing that c would be a root. Okay, so yeah, let's look at this. For our intermediate value theorem, we need f of x to be continuous on the interval a to b. Okay. Is f of x continuous on the interval from a to b? That'd be 5 to 6 here. And think about that for a second for yourself. And we should be able to conclude that looking at this function, yes, it is going to be continuous on that interval. And actually, this particular function f of x is going to be continuous everywhere. Because if you remember what we were looking at with different types of continuous functions, polynomials are continuous everywhere on their domain. And the domain of this function, which is a polynomial, is all real numbers. So this f of x is actually continuous everywhere for all the real numbers. So that's really nice. So we can justify that saying yes, okay? F of x is continuous on all real numbers because it is a polynomial. Okay, it's a nice little quadratic, so basically we're just looking at a parabola of some sort. Okay. You could even graph the parabola if you feel like it, but in order to use the intermediate value theorem, we don't actually have to graph the parabola. Okay, we just say our function is continuous everywhere because it's a polynomial. Now we need to show that our y0 value of interest, y0 equals 0, is in the interval from f of a to f of b. Okay, so we've checked off this part, f of x is continuous, and then show that y0 is a number between f of a and f of b. Okay, so show that y0 is between f of a, which we'll just call 5, and f of b, which would be 6 in this case. Okay, y0 equals 0. And so this requires us to just plug in those x values. So plug in 5, that'd be 5 minus 3 squared minus 7. Okay, so that'd be 4 minus 7, negative 3. There we go. And f of 6, do the same thing. 6 minus 3 squared minus 7. That'd be 9 minus 7, which is 2. Okay. So yes, y0, 0, is between f of 5 and f of 6. Yeah. y0 equals 0 is between f of 5 and f of 6. since f of 5 is negative and f of 6 is positive. Okay. So we've shown both of the criteria for our intermediate value theorem. All the things that are supposed to be true have been met here. And so we can say, therefore, by the intermediate value theorem, IVT, therefore by the IVT, f of x must have some value c in the interval from a to b, 5 to 6, where f of c equals 0. Thus, f of x has a root in the interval from 5 to 6, because that is what it means to have a root. All right, so that concludes the example. That's what it's asking us to do. All right, you can put a little box there to show that you're finished. But I wanted to include one more note here for you guys. Okay, so note. Something that sometimes frustrates people a little bit with this theorem. Notice that in this problem, we were able to say that, yes, f of x has a root between 5 and 6, but notice that we didn't actually find the root. We don't know what exact x value that root has. And that's the point I wanted to make here, is that the intermediate value theorem doesn't find the root for you. It doesn't tell you the value. It just shows that it exists. That's why we would say, yeah, the IVT is just for the existence of roots. All right. So yeah, the IVT is what we call an existence theorem. So existence theorem. Existence or existence? Okay, I spelled that right. Good. Existence theorem. All right. It just shows that a root exists. It doesn't actually find the root. Okay. It just shows that the root exists. It doesn't find the value. Okay. So you would have to use some other approach to find the actual value of that root. Set your function equal to 0 and solve for x. That is basically what you would do there. And then when you do that, you should get a value between 5 and 6. But yeah, the IVT is just an existence theorem. And so you might say, well, what's the point of that? I mean, can't I just set the function equal to 0 and find the roots, and then I know where they are and that they exist? And yeah, I mean, as long as the function is nice enough and you can actually set it equal to 0 and solve for x, then sure, go ahead, do that. That's great. Where this can come in handy is when you get to more complicated functions, things that you might not even necessarily have a closed function form for those. Like, you might not be able to get a nice, pretty formula. You might not be able to solve it when you set it equal to 0. So you can't always set equal to 0 and solve for certain functions when they get tough enough. So that's why the IVT can actually be helpful. If you're trying to find a root for some crazy function, you can't solve for the root, you can at least find values to give you an interval of where the root is going to be. And then if you can narrow that down enough, you can get close enough to locating your root for whatever project you're doing. So yeah, for those really complicated functions, the IVT is a more helpful thing.